This month, we are very pleased to invite Professor Dr. Andreas Buchleitner from Freiburg, Germany. So let me introduce a bit about Andreas Buchleitner. And he received his PhD degree at, I think, in Paris, right? Then he did his postdoctor in I think, Garching. Is that correct? Then from 1999 to 1907, he is a PI at the Max Planck Institute at Dresden, complex system. Then since 2007, he's become a professor at the University of Freiburg. He's now the chief editor of New Journal of Physics. And also he is a position of this executive board member of German Physical Society. So as you can see, he's kind of big professor. No, okay, he will be visiting here for 1 month. So his office will be in the second floor of this Q-Fort. So if you wish to talk to Andreas, to ask him any question, okay? So he'll be loved to talk to you, especially if you wish to study in Germany. Okay, so I think in the very beginning of this semester, me and Professor Zhongxian, so we ask you to take the note, 就是说接下来有这个礼拜，下礼拜没有，还有下下跟下下下哈，那他都会给这个基本的这个量子资讯的 lecture 哈，所以就是我们的要求就是要做笔记哈，那最后笔记要交上来哈，就是手写的哈，不是用手机哈，不是用手机哈。Okay, so I will try to remind Andreas to speak a bit slower. Okay. So if you have any question, please do not hesitate to raise your hand. Okay. Then he will answer your question. Okay. So if there's no further question, let's give Andreas a big hand. Okay.
Andreas is fine. And my email address, so as Yunan told you, right, you can find me in the second floor. If you don't find me in the second floor, you can write me an email to abu at uni, okay, uni freiburg.de. And so don't hesitate if you want to discuss something or whatsoever, you just drop me an email or you just find me directly, right? Then for the lecture, so I'm supposed to give 3 lectures, all 50 minutes. So it's a time slot which I'm not 100% used to, and it's also a bit maybe on the short side, right? So I have to compactify a bit, which then, as Yunan already anticipated correctly, might drive me to talk even faster. So if I'm talking too fast or something like this, you just do like this, or you give a sign and you just intercept, please, okay? And then I will talk slower for 2 minutes and then it will start again, but let's say you just insist, right? So then the general subject area is quantum science, quantum information a bit. However, I now picked for the 3 lectures, I have the intention at least to pick 3 different subjects which are important and which are, so to say, if you wish, so essential elements of the theory, and which come up again and again in many contexts, and which also have some connections which maybe you will emerge at the end in the 3rd lecture. And so the first will be, now today I will give you elements of what is called the James-Cummings model. Yeah, this is after a famous paper which was written by these 2 authors in 1963 or so. How about my handwriting? Is it large enough? Can you read it? Can you not read it? Who cannot read it? Ah, cannot read it. Okay, so I guess that's okay. So I will. So okay. So Jane's. Better? Okay, good. So anyway, this will, I mean, let's say if you cannot read something, ask me, I will spell it out, okay? And then the next lecture will then be the Floquet theory, which is in some sense a close relative of this theory, which I will present today. And these types of Hamiltonians or dynamical evolutions, which are described in the context of these models, they then give rise also to entanglement, or they can be used to create entanglement between different degrees of freedom of quantum systems. And this then, so some elements of entanglement theory will be the subject of the last lecture. Okay, so let me go directly now into the matter. So the Jaynes-Cummings model is a, if you wish, so it's a model of fully quantized light-matter interaction. Oops. Okay. Light-matter interaction. Yeah, and what do I mean by fully quantized? By fully quantized, I mean I will quantize, or I suppose that the material degree of freedom, which will be a very simple model of a very simple atom, right, as well as the field which is interacting with this material degree of freedom, both these constituents of the system I'm looking at, atom plus field, are fully quantized, right? So in some sense, this is also then, if you wish so, the typical setting of what people call quantum optics in a strict sense, because quantum optics, by the definition of the name or by construction, is about the quantum structure optical phenomena, right, of light. And so what we will have here, we will have the simplest model which describes the interaction between a quantized light degree of freedom and a quantized matter degree of freedom, right? And where both these degrees of freedom will be treated in an as simple as possible manner. So why is the model relevant? So first, let me say a few words about the relevance of this Jaynes-Cummings model. Relevance. Yeah. So yes. So I already said this, right? So the fundamental model. Yeah, and fundamental, at least for all people who are doing quantum science or quantum information. So who knows what a quantum computer is? Nobody.
I think everyone knows.
Everyone knows what a quantum computer is. So which are the constituents of a quantum computer? So when you talk to an experimentalist and you tell him or her, I mean, build a quantum computer, what does he or she need? Qubits, yes, qubits, right? And so you have these qubits, and then you have to make these qubits interact, and you have to control the state of single qubit, and ideally then also the state of several qubits, right? And so whenever, I mean, most of the theory which is done in this context actually relies on this model, right? So in this sense, it's certainly in this sense it's a fundamental model to describe dynamics of quantum mechanical. And now first I say a two-level system, right? I say it's a quantum mechanical two-level system. I will only later specify what is the physical intuition I associate with that. So two-level system. Well, I describe the dynamics of interacting with a interacting with a quantized electromagnetic. So QM is quantum mechanical, right? And EM is an electromagnetic field mode. Yeah, so we have a two-level system and we have an electromagnetic field mode. So now, can you give me some ideas of where in your quantum mechanics lecture you already saw two-level systems, quantum mechanical two-level systems? Where? Okay, so spin up, spin down, right? So I could have spin up, spin down. What else? What else? Look, 50 minutes. But however, we have to interact a bit. If I just preach like in church, it will be a little bit. You must be all believers, okay? So therefore, so what else? Where else? I mean, where are the solid? I mean, somebody who is preferring more solid state physics. Who are the solid staters in the room? Ah, bravo. Okay, so now, where in a very elementary model of solid state physics, or also of chemical physics, you would see something like a two-level system. So look, when you put the solid, right, you have this kind of periodic potential, right, which you can in principle put together as, I mean, the elementary thing is something like this. This is called a double well potential, right? And now, what in a double well potential, where there is a famous two-level system in a double well potential? What is in quantum mechanics, what can you do in quantum mechanics what you cannot do in classical mechanics? Quantum dots, bravo, yeah. But that's a keyword, right? So what can you do in quantum mechanics? In quantum mechanics, for example, there's a wall, right? So in classical mechanics, I cannot go through this wall, but quantum mechanics, I can get through this wall, right? And the wall is this, right? This is the wall, this is the barrier, a potential barrier. And how do you all this, I mean, penetration of a potential barrier in quantum mechanics, how will you call that? Tunneling, bravi. Okay, so now when you have, if this is now supposed to be a symmetric double well potential, right? So then locally in each of these potentials you have a ground state, right? And so you have two energy levels, left and right, which are degenerate, right? And which are coupled now through this finite tunneling barrier, so that the particle can tunnel. So what will the coupling through the tunneling barrier do with these two degenerate levels? I repeat my question. I mean, who did not understand my question because of my badly and rapidly spoken English? Please be honest. So who did not follow my question? Everybody followed my. Bravi. Okay. So who did not follow my question? Bravi, good. Okay, I repeat it. Okay, so now you see, here I have an energy level, right? Here I have an energy level, right? If the potential is symmetric, right? So this is just a symmetric copy of this one, then the energy levels have the same value, the same energy value. So they are degenerate, right? Now they are coupled through this tunneling barrier, which is finite. So there's a coupling, right? So therefore, I have here an energy level E, let's say 1, 0, and here E2, 0, right? So I have a matrix E1, 0, and E2, 0, but they are equal. So E1, 0 equals E2, 0, right? And now I have a tunneling coupling, which I write like this. So now so if E1 equals E2, and I have a coupling like this, V due to the tunneling, right? So what will happen to the energy levels? What will happen to this degeneracy between these two levels? It will be split. There will be a splitting. Yes. So there will be a tunneling splitting, right? Oops. There will be a tunneling splitting. Yeah, and this doublet, then you get a doublet of eigenenergies, and this doublet of eigenenergies is called the tunneling doublet, right? So this is also a two-level system, right? So you have a tunneling, so another picture would be this now, right? And then I'm an atomic physicist, right? So in atomic physics, then also, You could also, I mean, you could take either the tunneling doublet, right, which would then, I mean, if you diagonalize, then you would get these new, I mean, the blue ones would be the result of the diagonalization of this matrix, right? And where in this energy diagram how can I read out of this energy diagram the typical time the particle needs to tunnel? How is this time which I need to tunnel encoded in this energy diagram? How is the time I need to tunnel? So I assume I have my particle first here, right? And I ask, when will it be here? So this will need some time. So the time it will need to tunnel, how is it encoded in these energy levels which I chalked down there? I give you the energy levels, and then I ask you, okay, how do I get from the energy levels the time I need to tunnel? Was the question clear? Should I repeat the question? I repeat the question? Okay, so the question is, I give you the energy levels of this now lifted degenerate levels, right? The lifted degeneracy, so the blue levels here, right? And I ask you, now assume I place my particle first on the left-hand side. How long will the particle need to get to the right-hand side? And this is the time t, and I ask you to determine this time t from the given energy levels I gave you. Suggestions? Yes? You need some hint. You want? Okay, is okay. Bravo. Yeah, good. Yeah, nice. Yeah. So look. I mean, in quantum mechanics, right? When you have the spectrum and the eigenstates, you have everything, because then you can write down your time evolution operator, right? And energies per se, so something like e to the minus I e j t over h bar, right? This just gives a global phase which you cannot measure. So the only things you measure are essentially relative phases, right? Now, if you can describe the entire dynamics of your system in terms of just these two eigenvalues, you have just two eigenvalues, so there's just one energy difference, which is E1 minus E2, so the difference between these two, so the splitting, right? So it can only be the splitting which determines any relevant timescale in your system. So there is just one relevant timescale, which is given essentially by the splitting. And so it's then the inverse of the splitting, right? So the tunneling time is essentially the inverse. So if this here is, this is what we call the tunnel splitting. So let's call epsilon, right? Or 1 over epsilon. Okay? Clear? Question? Oh, good. Okay, prima. Okay, so right, and then so this would be the. Okay, I'm doing bad in time, but this doesn't matter. So and then the last thing for an atomic physicist, right? So you really think that you have a ground state of two atomic levels, and which you then baptize G or E, or which you could also baptize 0 and 1, right? If you prepare quantum computing language, but it's all the same, right? Okay, so that's the two-level systems, right? And then another purpose of why this is relevant, right? So that's what we already mentioned, is that we have it's a model to describe the dynamics of single qubits in quantum registers. Yeah, of a quantum computer. In a quantum computer, you would have, I mean, many of these two-level systems sitting in a register, right, and so on. So this would be the register, right? And you might have heard, you will hear at some point, right, that to run a quantum computer, what you essentially need, you need to be able to do any unitary operation on single qubits, right? And you need to do certain unitary operations on on pairs of qubits, right? And if you can do that, if you can do everything what you want with a single qubit, such a two-level system, right? And if you can do certain things with pairs of qubits, then essentially you can, I mean, construct operations on the complete register, and that's how you build a quantum algorithm at the end, right? And for describing the dynamics of such a single qubit, for this, the James-Cummings model is very nice, right? Or very useful. And then, last thing, I mean, maybe in some sense also useful for quantum computing, but not only, it's also the James-Cummings model gives you, in some sense, the prescription for describing the elementary process to exchange excitations between distinct degrees of freedom. Yeah, and these distinct degrees of freedom will here be, on the one hand, the two-level systems degree of freedom, and the electromagnetic field's degree of freedom, right? So for just to read it, elementary, I mean, let's say the James-Cummings model, its relevance is due to one of the reasons why it's relevant is that it's a good model to describe elementary process to exchange excitations between distinct degrees of freedom. There's something you cannot read? Okay, good. Okay, so now, so anyway, I'll run out of time, but I just now. Now I first will remind you of a few things which we need. So I will not do all the technical derivations, right? I will just put some intermediate, show you some intermediate steps, but I will remind you of what you need as ingredients for the, we do in the following. See, looks like I'm missing. Okay, yeah, good. Anyway, so ingredients. Yeah. So first, the two-level system, the quantum mechanical two-level system, quantum mechanical two-level system. So somebody mentioned already spin up, spin down. So which are the objects, typically, which are the mathematical objects you use to describe a spin-up, a spin-1/2 system in quantum mechanics? There are objects which you use to describe operations on them or to describe certain properties, observables, typical observables on a spin-1/2 system. You all heard that already. Just, I mean, Matrix is always good, yeah. Matrix is always good because it's an operator, it's a matrix, yeah. But now it's a two-level system, right? So what will be the dimension of the matrix? 2, right? And so now, which are the matrices which you, I mean, often hear about when you operate on a spin-1/2 system? Pauli matrices, Pauli, yeah, prima. Yeah. Okay, so we have the so we write it like this: E and G, right? And E we write we call it. Or as a two-dimensional vector, we define it as 1, 0, and G we define as 0, 1. And then the Hamiltonian of the two-level system be H, and I write H, AT for atom, right? Because later I will imagine the two-level system to be realized by an atom or by a model of an atom. And this is just 1/2 omega, and then the Z Pauli matrix, right? Which I don't know whether you know this notation or whether you know the quantum information notation. The quantum information notation, bless you, the quantum information notation would be a capital Z, right? So, and then, so, okay, so I chalk it down. So sigma Z equals 1, 0, 0, minus 1. Sigma X equals 0, 1, 0. Sigma Y equals 0 minus I 0. And then the identity, which I don't write down now. Another object which we will need is, which is important, is sigma. Also from time to time sigma minus, but I write it just as sigma, which is 1/2 times sigma x minus I sigma y and sigma plus or sigma dagger equals 1/2 sigma x plus I sigma y. Okay. All right. So that's the ingredients we need for the two-level system, right? And I will not now write down the action of the Hamiltonian or of the Pauli matrices on the different states. What is important, however, is that, I mean, maybe one thing is important. What does sigma when you apply it to E? I mean, who has not yet seen these two operators here? Who has not yet seen these two operators? Everybody has seen them. Very good. Okay. So now, what does sigma do with E? To G, right? And what does sigma do with G? 0. 0. Which 0? I mean 0. So is it? I mean which? I mean 0 is a neutral element, but in which space now? Is it a scalar 0? It's the neutral element in the vector space, right? So that's important. Okay. So 0 is good. That's what typically people say, but it's important to realize that this is the neutral element in the vector space, right? In the two-dimensional vector space, right? Precisely, right? And what does sigma plus do with E? Somebody else? Also 0, right? Okay, good. And the other ingredient, so there is one ingredient which, I mean, so to say, the toolbox which we need to describe the two-level systems, and then we need the toolbox to describe the quantized one-dimensional harmonic oscillator. Quantized one-dimensional harmonic oscillator. Yeah, and often we'll just write HO. And as a picture, right, it looks like this, right? So that's the energy levels. They are equally spaced, right? Yes, okay, so I'll leave it like there. So the Hamiltonian is HO equals, and now I write it immediately in terms of creation and annihilation operators, A dagger plus A dagger A plus 1/2 times the identity. I mean, in general, I will not write the identity here. It's just for formal correctness or consistency, right? And omega here is the oscillator frequency, right? And I write it capital omega because later I will also write, I mean, I could introduce it already here. So later I will write this as small omega, and at some point I will compare these two frequencies, right? And so that's why I need two different variables, right? So now we know with A dagger equals identity, and then the eigenvalue equation H upon, how did you call these states? N, how do you call them in the context? How did you call them in the context of the harmonic oscillator? Fock states, right? Number states, Fock states, energy eigenstates. Yeah. So Hn equals H bar omega, and then N plus 1/2 N, right? And N is going through the integers, positive integers, including 0, right? Right, and then we still need the action of A dagger upon N gives what? Suggestions? N plus 1? N plus 1, yes, but still something. So acting upon N gives me the eigenstate N plus 1, right? But do I need a prefactor? Of N plus 1, yeah. okay, look, what we can try. I mean, let's say, of course, I will forget it anyway. But let's say, still, still we can try. Maybe if you say something, maybe you give me your name, and I will try to remember, which is an additional difficulty because it's Chinese, right? So it will be very difficult for me, but still I could try. So which are your names, please? Bo Yan. Zihao. Okay, I'm sorry for the bad pronunciation. Okay, so square root of n plus 1, right? N plus 1, yeah. And then a, right, upon n gives square root of n, and it decreases the excitation, right? And then a on the zero photon Fock state, what does it give? 0. Which 0? In which space? No. It's the neutral element in the vector space, right? I mean, you have an action in a vector space, right? So it maps you on 0, but this is the neutral element in the vector space. Okay. So, okay, good. So that's the basic ingredients, and now the idea is, right? So what do I do with time? So first, the idea is to dilate time. But anyway, so let me see how I do that. Okay, so I stop in between, and then next time I connect it to the Floquet model. That's fine. Okay, so then we can take this away. Okay, so now in principle, right, we have this two-level system and we have the harmonic oscillator, and that's the two distinct degrees of freedom of which I spoke in the motivation part, if you so, right? And now we want to transfer essentially excitations between these two degrees of freedom. That's all the purpose, right? And we want to have a reliable way to do that. Idea. Okay, so we had relevance, then we had ingredients. Now we have the idea, reversibly transfer a single excitation quanta so in a sense, the smallest unit of energy which you can think of transferring between different degrees of freedom, so then of the order h bar omega, right? Between the electronic, because the two-level system will become a two-level atom, right? And in the two-level atom is essentially the energy eigenstates of an electron bound to a nucleus between the electronic and the field degree of freedom, DOF. Okay, DOF, degree of freedom. Okay. Now, if you can rephrase that, but it doesn't change the substance, but it changes the kind of propaganda you want to make, right? So you can also say you want to store quantum information in a convenient degree of freedom. Right? So, for example, sometimes people talk about flying qubits and stationary qubits. The flying qubit would be, for example, photons, right? Or would be stored in photons. And the stationary photon qubits, so to say, to do something like a memory for quantum information, would be atoms or atomic vapors, for example, right? And so now, I mean, let's say when we want to transfer single quanta of energy between different degrees of freedom, so what's our intuition? So when, assume you have 2 degrees of freedom, right? Now you couple them and you want to transfer energy between them. What do you think is the most efficient way under which, or what should you do to efficiently transfer excitations between 2 degrees of freedom? And maybe, I mean, let's say, of course, you think, I mean, you should always think in your picture of the world, right? But let's say, under the assumption that your picture of the world might be still a little bit more classical than quantum. So think about a classical, not every day, but almost every day, transfer energy between 2 degrees of freedom. The dynamical system. So when you now, when you are, I don't have an experiment here, no. But let's say if you have a swing, right? So there's a child on a swing, right? And or you are on a swing. Anybody, I'm on a swing, right? So now you want to, I mean the swing. I'm in my ground state, so the swing is not moving. Now you want to transfer energy into the swing, right? So what do we have to do? Push, yes, push, correct, right? So, wait, what was again the name? Sorry, I have to. Boyan. Okay, thank you. Okay, Boyan, yes. Push is right, but push how? How to push? I mean, strong, of course, yeah, but let's say, I mean, you have the swing, right? And the swing is making a certain motion, so now, but how do you, I mean, let's say if you push like this and the swing is going like this and you push like this, will it work? Will it? No. If you, what? Same frequency, okay, bravo. So how do you call that when you do the same frequency? When you drive a system with its close to its eigenfrequency, how do you call that, this condition? Resonance condition, right? So now, where do you do this in your classical mechanics class? So what is the problem which you deal with in your classical mechanics class when you do that? So what's the simplest model of that? I mean, let's say now the swing, when the swing has small excursions, at small excursions of the swing, right? The swing is essentially a pendulum, right? So this is the pendulum, right? And now, now the pendulum, of course, goes slower when it's here, right? And so, but when it's here, right? So there's a certain approximation to the pendulum. How do you call that? The small excursion approximation to the pendulum around the stable fixed point, around the stable equilibrium. Ah, bravo. Harmonic oscillator. Zihao. Okay, good. Zihao. Thank you, Zihao. Okay. Okay, bravi. Okay, so the idea is essentially, bless you, so that the most efficient way or the most efficient coupling between both degrees of freedom, EOFs, at resonance. Yeah. And this means that now we will have this harmonic oscillator. Now we will use the harmonic oscillator to drive the two-level system, right? So at resonance, this means the frequency of the driving force is similar or close to the eigenfrequency of the driven system. So essentially at resonance, it is, we will look somewhere in the vicinity of small omega equal to capital omega, right? Why is the transition frequency something like, why is the transition frequency to be associated with the eigenfrequency of the system? This is just a question which comes to mind. So it's a transition frequency, right? So it's a difference between the two eigenstates. And what does this have to do with actually a classical frequency in the atom? right? I will say this later again, right? But I will take, if I do a two-level atom, I select two levels of a real atom, which has many levels, right? And now let's take the hydrogen atom because it's the simplest one, right? So now, what is the statement of the correspondence principle about the meaning of the, or encoded in the correspondence principle about the meaning of the distance between two adjacent energy levels? Did you hear already about the correspondence principle? Who already heard about the correspondence principle? I write it down. Correspondence principle. So correspondence principle. So apparently something has to correspond to something else, right? So the correspondence principle is about the correspondence between classical and quantum mechanics in a certain limit, right? And so one of the formulations is due to Bohr, right? And this says that the energy spacing in the quantized system corresponds to the classical Kepler round-trip frequency in the Kepler model, right? So you know that the electrons go around the nucleus like planets around the sun, right? But the electrons in the hydrogen atom can only have discrete levels, right? And then the correspondence between the classical mechanics and the quantum mechanical energy levels is that the energy spacing corresponds to the eigenfrequency, that's why I was asking it, right, of the classical system. So this just as an association, right? Okay, and so where do we know this from, right? So recall a classical driven harmonic oscillator. Yeah. Okay. Good. Yunan, I have 5 to 10 minutes left, something like this, or 10 minutes. 10 minutes. Okay. Good. So then what I do is I just will formulate the Hamiltonian. I will continue with this next time when I do the Floquet. I will connect it to the Floquet theory next time. Okay. So now, I mean, we have the relevance, we have the ingredients, we have the central idea that we will have to go near resonant, right? And now we need a mapping between. We have to make these things concrete. So we have a mapping, which I already anticipated by coming up with this association with an atom, right? So the two-level system will be realized by choosing two discrete levels of a real atom. How many levels does a real atom have? Infinitely many levels, right? So it has an infinite spectrum. I mean, it has an infinite number of discrete levels, and it has a continuum of levels. So it's even worse, right? So therefore, it's actually not simple to isolate a two-level system in an atomic system or in other real physical systems. That's one of the reasons why, I mean, let's say it took so long to be able to even think about building quantum computers, right? So the real atom is something like a continuum spectrum, right? And then you have this Rydberg series, right? The discrete states. So this is, for example, now let's assume this is hydrogen-like atom, right? So then you have the Rydberg series. The eigenvalues go how? What's the Rydberg progression? N squared. And this is not a full, I mean, 1 over 2n squared, right? Yeah. In suitable units, precisely. Yeah. So and then what you do, right? Now you have to pick, in some sense, for example, you would try to select these, right? And this then would give you your two-level system. G, E with E, minus Eg equals omega. Right? And let's say this isolation of these two levels out of infinitely many, right? This is actually highly non-trivial. Right? So it's not easy, right? And for example, it only can be done also, it only can be achieved over finite time spans, right? And nowadays when people see that quantum computers don't work, they have still finite errors. One of the finite errors you typically make is that there are other levels in the vicinity which you do not take care of in your two-level model, right? But which spit in your soup in some sense, right? And then, okay, 6 minutes. So this is the two-level system, right? So this will be two discrete levels of a real atom. So then this is then a two-level atom. Yeah, which in principle doesn't exist, but in a certain approximation it does, right? And you must always be aware of this approximation, right? And then the one dimension, we still need now the other ingredient, which is the harmonic oscillator, right? So, and for the harmonic oscillator, let's do it here. So 1D dimensional quantum mechanical harmonic oscillator. Okay, so I told at the beginning, right, I'm a quantum optician, so I'm used to work with light. So therefore, now the harmonic oscillator will be realized by a single mode of the quantized radiation field. And so now, but let me ask you experimentally, how do I isolate a single mode of the radiation field? So what's the radiation field, right? The radiation field are the plane waves, which, for example, go around here, right, in all different directions, different frequencies, different directions. And typically one way to define modes of the electromagnetic field are through their modes, right? And the mode would be characterized by the wave vector, right, the direction, right? Then the frequency, what else? I'm still missing something. What do I still need to fully characterize a mode of the electromagnetic field? When you have a plane wave, for example, it has which properties? So I tell the experimentalist, okay, so I need this, I want this direction, so this wave vector, excuse me. This direction, I want this frequency, but what still do you have to tell the experimentalist to fully define the mode? Polarization, prima, super, yeah. So, okay, so the, okay. So now how do you isolate? How do you isolate now? You have many, I mean, in this here you have a continuum of modes. So when you want a single one, what do you do? Any ideas? You want to, I mean, for example, you want to select a certain frequency, a certain wavelength. What do you do to select the wavelength from the radiation field? I mean, look, you get a continuum when you have no boundary conditions, right? So when you have a free electron, you have a continuum in the atomic model, right? But as soon as you see boundary, as you put a boundary, right, boundary conditions, then you quantize, right? So you confine the field and you put mirrors, right? So then what you could, for example, you put two mirrors, right? So these are supposed to be mirrors. Yeah, and then, for example, there's just this, I mean, you have vanishing boundary conditions, right? And then you would select only certain wavelengths would fit in there, right? So because you can only have integer multiples of half wavelengths which can fit, right? And so this gives you a discrete spectrum. And so then this is the way how you experimentally, so there was a Nobel Prize by Serge Haroche, right? I think in 2012 or so, right, who did this and then, I mean, populated these modes by single photons, right? And So now this, such a single mode then is essentially this harmonic oscillator will be represented by this harmonic oscillator we have up there. So why is it plausible? I mean, who has already seen field quantization? Anybody has already seen the quantization of the electromagnetic field? You have seen that? Who has already seen that, the quantization of the electromagnetic field? Nobody. Okay, prima, good, okay. So there, then the idea is, I will not do it in detail, right? But I'd say, you know, I mean, what is the energy of the electromagnetic field in a certain volume of the free, charge-free, no charges, no sources, no currents? What's then the energy of the electromagnetic field in a certain volume? Okay, it's a volume, so it will be some integral over the volume, right? Over space. And then, do you remember, so the electromagnetic field has a magnetic field component and an electric field component. And do you remember which is the form of this Hamiltonian, or of the integrand now in terms of the E field and the B field? How long is the electromagnetic class ago? Electrodynamics class?
They took this in the second year of undergraduate.
So which is
2 years ago.
It's long ago, too long, right? So it's clear, right? So this is essentially then E squared plus B squared. Yeah, and this makes it at least plausible that this is a quadratic form, right? And now you have this quadratic form. Then you define essentially your canonically conjugate variables Q and P, momentum and position, right? Which then you can rewrite as a harmonic oscillator, or as a sum of harmonic oscillators. And so to say, then the contribution of a single of these specific modes, right, is then just a single quantized harmonic oscillator. So that's essentially the path we will go to. Okay, so now let me just chalk down. Let me just chalk down then the model Hamiltonian, and I will do it then in 2 weeks. I will continue in 2 weeks. Okay. Because I think I have 1 minute or so, something like this, right? No, I will do it now. I will be fine. So then now we put everything together, right? So we have the Hamiltonian for this two-level system. We have the Hamiltonian for the single quantized mode of the electromagnetic field, which can be actually written as a harmonic oscillator, a one-dimensional harmonic oscillator. And then we still need to couple them, right, resonantly, as we said, because we want to transfer efficiently the energy between both degrees of freedom. So therefore, then the total Hamiltonian of the interacting two-level atom and single light mode writes as follows: H equal H atom, which I wrote up further up, right? This was 1/2 times omega times sigma z, right? Plus H harmonic oscillator plus and now comes the interaction, and the interaction V, right? This I still have to specify, right? And with this I will stop. This is the last thing. Now the force, right? The force on an electric, so V, so classically, let's say, so in classical electrodynamics, right? So now I imagine I have a driving field with frequency capital omega, right? And so this characterizes my field mode, right? I have a certain amplitude F. Certain amplitude F, where is it? So I have then the amplitude is the force per charge, right? So then the force on the electric charge is minus E times F, and times X is the potential times cosine omega t, capital omega t. Yeah, if X is the direction of the field polarization. So if F is now my field amplitude, my oscillating field vector, right, parallel to X direction, right? And now I translate that into this quantized version, right? And so now X is the dipole, is the atomic dipole. So E times X is the atomic dipole, right? So I will set E equal to 1 at some point. I will absorb it in some abstract constant, right? So therefore now I replace F cosine omega t by A plus A dagger, which are now, right, A plus A dagger are the familiar annihilation and creation operators which you know from your harmonic oscillator, right? You know also that A and A dagger, how are they related to the position, the canonically conjugate position and momentum variables in essence? Roughly, it's a linear combination, right? It's something like Q plus IP, and then there's omega sitting somewhere to get the units right, or the dimensions right? So therefore, you see that this is actually proportional to P in essence, right? To something which is proportional to the canonical momentum in the representation of the field, right? Minus EX, right? This will be now represented by H bar G. The H bar just I put there to make it explicit for notational purposes, if you wish so. And then sigma plus sigma dagger, which are the raising and lowering operators of the two-level systems which I had above, right? And so this essentially says that this dipole coupling, the dipole operator couples the excited state to the ground state and the ground state to the excited state, right? And so therefore then here I get at the end the following Hamiltonian. Let's say, okay, so let's write it in full beauty. So this was, I think, 1/2 omega times sigma z, right? Plus A dagger A plus 1/2 H bar omega, right? And then plus H bar G times A plus A dagger times sigma plus sigma dagger. Okay, and then now we leave it here. So this is now the full Hamiltonian of the interacting of the dipole coupled two-level system and single mode quantized field, right? This is not yet the Jaynes-Cummings Hamiltonian. What we'll do now next time, and then lift it to the Floquet level at some point, is we will look at the Schrödinger equation, which is generated by this Hamiltonian. And we will get its solution in the interaction picture. So what's the interaction? What do I do when I go to the interaction picture? What's the idea of the interaction picture? Last question for today. Maybe before last question. Last question, before last question. So I have the Schrödinger picture, I have the Heisenberg picture, and I have the interaction picture. So in the Schrödinger picture, which objects in my quantum description carry the time dependence? The Schrödinger picture. States, yeah. Provided the Hamiltonian be time independent. Now here I have a time dependent Hamiltonian, so it's getting a bit more complicated, but in principle like this, yeah. And then in the Heisenberg picture, the operators, right? And now in the interaction picture, both, yeah, right? And so now, I mean, what do you want? Which time dependence do you want to map on the operators? So look, I mean, the interaction picture is, I mean, let's say here you say, I mean, that's the unperturbed Hamiltonian, the non-interacting system, right? And that's the interaction, right? So now essentially you replace the Schrödinger picture by the interaction picture. So this means that now the states should only carry the time dependence which is generated by the interaction term, right? And the operators should carry the time dependence which is carried by what you already know. It's the unperturbed system. So the unperturbed system, you always assume that you know, or you have already diagonalized it. You know the eigenstates, you know its time evolution. So it's boring, right? So therefore, in the interaction picture, you essentially absorb it in your coordinate system, right? The coordinate system being the eigenstates of your operators, right? And so the coordinate system may rotate in some sense because the operators have some trivial, already known time dependence, right? And you're only interested what on top of that is caused, I mean, how on top of that the states are changed with respect to this already rotating, trivially rotating coordinate system, and this is generated by V, right? So therefore then in the interaction picture, the Schrödinger equation has which form? In the interaction picture, the Schrödinger equation has which form? So left side, okay. So Schrödinger equation, IH bar dt psi Schrödinger equals H S psi S, everything in Schrödinger picture, right? Now Hs equals H naught plus V. So then in the interaction picture, IH bar dt psi in the interaction picture equals what did I say? I said that, let's say, in the interaction picture, you want that the non-trivial time evolution is generated only by the interaction term, right? So therefore here sits V. Now the representation of the interaction term in the interaction representation which generates the dynamics, right? And that's what we will look at next time. So I thank you for your cooperation and also somehow interactiveness, okay? So see you in 2 weeks. Yeah. And if you have questions in between, I mean, let's say, as I said, write me, see me, whatsoever, right? Do you have questions right now? No. You want lunch? Okay, enjoy your lunch. Yeah.